So good afternoon, everyone. So can you all hear me at the back? Okay, cool. So how many of you like machine learning? Nice. How many of you use scikit-learn in Python? Okay. How many of you have used H2O? Okay, cool. This is H2O for beginners. So I will start with some really simple example. The main objective of this workshop is to get you started. So we're not going to know really deep details of how to use H2O for advanced features, but I want to get you just started. So getting a data set into H2O, try to do some machine learning from that, and this is to get you started. So as I said before, if you want to download all the materials, this is the address to download tutorial materials. So let's go through the agenda. So I've been here 3 times. I've been here in Berlin 3 times. So every time the weather was really, really nice, except yesterday and today. So luckily I'm here. So let's go through this tutorial. So first of all, I want to give you a really quick introduction of the company and the machine learning platform that we have. It's also called H2O. And then we will move on to the hands-on tutorial that you will have all the Jupyter notebooks and all the data in that GitHub repository. So the first half is only for beginners, so it's mainly about the basic usage of H2O in Python. And then we will have maybe a 5-minute short break. And then after that, I'll go on to a bit more advanced feature of H2O. It's as if I'm trying to use H2O for data mining competitions. So a little bit information about myself. So you can see that I wasn't a computer scientist or data scientist by training. So I've been in the civil engineering industry for nearly 10 years. So somehow I discovered H2O about 3 years ago. And then a few things after that, I become a data scientist. So this could be one of the reasons that you may want to try H2O today, because it's easy to use. It will help you to lower the barrier of machine learning. So you can try to some really, really advanced stuff, but with simple APIs in Python and in other interfaces. So after my civil engineering journey, so I went to become a data scientist. I worked for Virgin Media, a telecom in UK, and Domino Data Lab, another company in US, before I joined H2O about around February last year. So this is how I met H2O. So I went to a conference back in 2014. This is the UseOut conference in UCLA. So I heard about this company called H2O. So at that moment I thought it could be someone crazy or someone really, really smart. So to use H2O as the name. So I gave it a try, and I never regret. So I went on to wrote a blog post, to write a blog post about how to use H2O, Domino, and how to do data mining competitions. They call Cargo platform. And that's how I joined H2O. Okay, so let's talk about H2O.ai. So H2O.ai is the name of the company. So we are a young company. So we are founded about in 2011, and then we get about 70 people at the moment. So the headquarters is based in California. It's based in Mountain View in California. So I'm one of the 2 guys based in UK. And then we, from 2014, when I first discovered H2O, I think they have the momentum in terms of getting more users and more customers. And you can see that there are many of the top companies in US, they're using H2O. And these are some phases that in H2O. So you can see that we have a really good balance between male and female. So we try to get to 50-50 in H2O. And that's me down there. And we are so lucky to have 3 legendary professors from Stanford as an advisor, because we implement some of our algorithms from scratch in Java. So we need someone as experienced as them to guide us through the journey. So this is how they work in the headquarters. So this in the middle is Arno. Arno Canto is our CTO, and then the professor around him just to try to improve some of the algorithms in H2O. Oh, by the way, this is a more interactive section. So at any time, if you want to ask questions, just please raise your hand, and I'll try to repeat your questions. Okay, this tutorial is mainly about the H2O machine learning platform. So we do have other products like Deepwater, which is our GPU deep learning. Sparkling Water is our integration with Spark, and Steam is other surface that we can help you deploy your model. But this tutorial today is mainly about the H2O platform. Okay, so let's talk about the platform. before I move on to the actual details, I want to give you some reasons why you want to try H2O, like either during this workshop or after this workshop. So I'm going to use a benchmark from Szilárd Pávka. So he's not working for H2O. He's a data scientist in LA. So he did a benchmark using different implementation of GBM or gradient boosting machines in R, in Python, in Spark MLlib, in H2O, and in XGBoost. So what he found is that one of the key points he found is that when you have bigger data, so it turns from 10,000 data points or rows to 10 million, H2O is the fastest when you have big data. And we didn't sacrifice the performance. So in this case, we're using AUC, the area under curve, as a metric to measure the performance. So we didn't sacrifice the performance for speed. So this is one of the reasons why you may want to try H2O, because it's very high performance, scalable, and powerful in a way when you compare to other implementations of the same algorithms. So what is H2O? So this is a really high-level architecture of H2O. So you can see that from left-hand side, you have different connectors to database or other files. So today we will start with a total data set in CSV. But if you are feeling comfortable with H2O in the future, you can move on to Spark, Hadoop, or other database in your company. So there are many ways to connect your data to H2O. So in the middle, you can see that the yellow rectangle in the middle is the heart of H2O. So all the algorithm in H2O is written in Java. So this is for high performance and scalable algorithm in the computer engine. So this is a machine learning platform. So you can expect to do many common tasks that you would do for machine learning. So including importing data, look at the data, train a model, so either supervised or unsupervised model, export the model, and make some predictions. So this is just a platform, a generic platform, machine learning platform that you can do with many different kinds of problems. And because we know that not everyone likes to use Java, so how many of you use Java for work? Okay, so not too many of you use Java. So we realized this is the problem, so we want to create different interface, different APIs for different users. So people can use, today we're using Python, or you can use R in the future. You can use even the web interface that I will show later on to use H2O with different kind of interface. And some people can stop right there. So if you have a model in Python or R, you can stop there. But some people like to bring it to productions. And that's why we have the last part here. So we can export the H2O model as a single Java file. And then that file, you can put it into a different machines for scoring or for in a different pipeline. So that's what we're trying to focus today is one of the interface of H2O in Python. Before we do that, I want to quickly show you, this is the web interface of H2O. So people, so maybe your colleague or your friends, they may not like to use Python, they may not like to use R, any programming language. You can give them this interface using just the web browser and to use that to interact with H2O. So you can still do most of the features. You can use most of the features of H2O with the web browser. That include importing your data, build a model, and export the model, and make some predictions. But we are focusing on the use case in Python today. And just a bit more about the algorithm itself. So everything is written in the manner of distributed manner. So everything that you do today, maybe on your single machines or your laptop today, but if you want to use H2O with multiple clusters, multiple machines, multiple nodes, it is the same kind of code. That's the same thing that you did today on your laptop. When you move on to a bigger cluster or with more CPU power, it will automatically distribute it across all the CPU resources that you assign to H2O clusters. That's automatically done for all the users, so you do not have to think about how to optimize that parallelizations for different structure. It will just do it for you. Okay, so that's a really quick introduction of H2O company and the H2O platform. So now we just move on to the hands-on tutorials. Is there any questions before I move on to this tutorial? Is everyone happy? Have you all got the materials on your laptop? So I won't ask you to run the code today in real time, because I prepare all the Jupyter notebooks on GitHub repository or on that USB stick. So you can just look at the result and look at how I explain the logic to you. So the key objective of this workshop today is to get you started with H2O. So I want to tell you how to start the H2O cluster with Python. I want to show you how to import data frame in different ways. So you can use a local CSV file. You can use something from the internet. I want to show you how to perform some basic ETLs or some basic data transformations and how to export data in Python. I want to show you the basic API to train regression model and classification model. These are the two very common tasks in machine learning. And after that, that's the basic one. So after that, I want to show you how to evaluate the model performance and how you can tune it to improve the performance of different algorithms. And at the end, I want to show you how to use one of the key features in H2O to stack the model together. And this is one of the really a key trick to improve your performance for data mining competitions like Kaggle. I will also show you briefly how you can deploy H2O in the cloud. So because H2O is written in Java, you can just deploy it on any machine with Java 1.7 or Oracle 1.7 or OpenJDK. OK, so again, this is the link for tutorial. Let me just show you the real thing in the web browser. So see that if you go to this repository, you can see the actual tutorial and an introduction to machine learning. There are lots of Jupyter Notebook here for, you can see the Py one on the top. They are the example in Python. But if you are also interested in using H2O with R, you can see that the bottom few ones are written in R. So we'll start with the first one. The first one is just showing you how to initiate a cluster of H2O and then import some data into it. So let me just go back to one. So if you're on GitHub repository now, you can click on the first one. So the 0 oh, I don't have connection. I'll just go through the slide from here. It's fine. OK. Oh, of course, one more thing. How many of you have installed H2O before this session? OK, 1, 2, 3. Don't worry about it. So it's not that difficult to install H2O. So all the instructions are online. So if you go to h2o.ai/download, then you can find the information about how to download H2O and install it in Python. So basically, it's like this. If you can see, maybe it's not that clear, but it's basically just a few dependencies in Python, and then you install Python view in your Python distributions. It's nothing really complicated to install H2O. You can think about H2O as a module for your Python module on your computer. So assuming that you have H2O installed, then we can move on to the actual work. So you don't have to do anything right now. You just have to look at the Jupyter Notebook on your laptop, and I'll just go through the key step and explain to you the logic behind different steps. So the first part is to start and connect to H2O cluster. The reason why is that all the computation is done in Java. So when you execute the code in Python, it's not using Python to do the computations. It's using Java to do the hard work. And that's why we need to initiate a cluster in terms of a Java virtual machine or JVM. So that is the command. So when you have H2O installed, you just call the module or just import the module as H2O. So import H2O first. So the second command is h2o.init, so initiate a cluster. So the argument in that is nthread, so number of virtual core. You can say virtual core. So maybe if you have a quad-core computer, you may have 8 virtual cores. So if you put on the number, the actual number in there, maybe 4, 5, 6, it will then allocate that resource to the H2O cluster. But if you don't know how many virtual core you have on that machine, you can simply use -1. -1 is like the automatic detection. So we just go through your system spec and look at how many virtual cores that you have on that computer. Then we use everything. So once you have that, then you will see something like this. Maybe you can't see quite clearly, but this is like the information of the JVM, the Java virtual machines. So you can see how much memory is allocated to that JVM, how many virtual core is allocated to that JVM, and et cetera, et cetera. And you can also see the IP address. So that IP address and the port number is all you need to connect to the H2O cluster, or using web browser, or using R or Python. Are you guys OK so far? Yeah. So this is just to start a cluster on your laptop. So we are still doing the things in the same notebook. So the next step, so once you have the cluster in the memory, next thing you can do is to import some data. So I want to show you 3 ways to import data from a CSV file. So the first way, the most easiest way, is that you have the CSV file on your hard drive or somewhere on your laptop drive. So you know the exact address of that file. So what you need to do in H2O is using the H2O.import_CSV, and then you point it to the path of that file. So in this case, I have this wine quality CSV in here. You can find it in the GitHub repository. And after that, you can just do the same thing that you would do in Python. You can look at the first few rows using .head command. Then it will show you the first 5 rows of the data, as you can see it here. So, but sometimes you want to have some data stored on the internet, and you just want to download it directly from the web. So you can do the same thing. You can use the same command, so H2O.import files. But then this time you provide the full address, the full URL of that file online, and we'll just do the same thing. You just download the thing and then import it into import it into the H2O cluster. And again, you can do the head, so you can look at the first few rows. And sometimes this is when you do data munging in Python first, so you want to use Panda, so that you have lots of procedures, a lot of the pipelines to clean the data, to transform the data, to create different features. And once you're happy with the final data frame in Pandas, you can use H2O, you can use a command in H2O to convert that Panda data frame into Java, into H2O data frame in Java. So the command is, if you see in the bottom half in there, is H2O frame. So that is to convert anything in Panda data frame into the H2O cluster, which is in Java. So that is the way that you can convert anything from Pandas to H2O data frame. Okay. Are we okay so far? Yeah. So that's some basic way to import data set. So now we have the way to import it, so we can now do some exploration or transform some of the data. So we are going to move on to the next Jupyter notebook. So if we go to the pi_02, the data manipulation notebook, so we are going to discuss some ways to explore or to transform the data once you have that imported into H2O. So first of all, I'm going to use the classic Titanic dataset. So this is a CSV, again, in the same GitHub repository. So when you have that there, you can just do a head and look at some of the records here. So you can see there's some information about the passenger on that on Titanic and whether they survive or not. So first of all, we can do some basic thing to look at the data. So if you can see that from this table, the second column from the left-hand side is about survived. So it's always 0 and 1. So it's in H2O as integer. But we know that, so with our previous experience, we know that this is like a binary classification. So it's yes or no. But H2O doesn't know that. So in order to do that, we have to tell H2O that this is actually a categorical label instead of integer. So first of all, we want to do a histogram and look at whether there's just only 2 unique values. So we do the .hist and then blanket, and then you can see that it's just only 2 unique values in that column. You can also use the count functions or the table function in Python to look at how many counts of each class. So for 0, we got 549, etc., etc. So we know that there are only 2 unique values. So now we can tell H2O, we can change it from an integer to categorical value. The way to do it in H2O is to use the as factor blanket. So this way, H2O will know that this column here, survive, is not integers, it's a categorical value. So when you do the classification, you know that this is a binary classification instead of a regressions. Just saying that if you can do a summary as well. So for all the things in the H2O data frame, you can do a summary, and then we give you some information about maybe it's the type of data, the missing values, max and min, etc., etc. So this time you can see that it becomes elem. Elem is the type of categorical value in Java, and that's why they use it in here. It's called elem. Okay. So similarly, we can do the histogram on a different column. So this time I want to look at the class, so passenger class in there. So again, we can see that there are only 3 different values in there. So 1, 2, or 3. You can also use a table to do the same thing. Just look at the count of that. So that is some basic stuff to look at the data. Everyone okay so far? Yep, okay. So now we look at some data set. So we can move on to the next step, I want to show you how to use H2O in Python to train the regression model. This is some of the algorithm. These are some of the algorithm that we have in H2O. So now let's focus on the left-hand side. It's a supervised learning problem. Because we have the label, we have the final answer, the response in a data set. So we want to use the supervised learning algorithm in this case to build a regression model. So we have very common algorithm in H2O. So GLM, the generalized linear model, the random forest, GBM, the gradient boosting machines, and deep learning. So that's some of the most common algorithm that you will find in other packages, so in R, in Python, in other languages. But we implement all this from scratch, and we optimize it in Java. So this is a more high-performance algorithm, although it's similar to what you saw in other tools. So I'm going to show you how to do this model in H2O. But sometimes you want to dig deeper and want to find out more information about each algorithm. So if you go to this website, the DOCS, which is documents.h2o.ai, so you can find a lot more information about H2O and H2O algorithms and everything about the features in H2O. You can find from this single website. For example, here, if you click on the reference of GBM, then it will show you more information about GBM, what it is, what it does, and what's the limitation of GBM. OK, so let's go back to that regression problem. So we're going to use the same the wine quality data set, again, that we saw in the first example. So what we're trying to do this time is to use the features. Say on the left-hand side, you got 11 features about the wine, so there's different characteristics of a wine. And then at the end, we have the quality. This quality is a number that the people assign to this wine. So they say from, I think it's from 3 to 9, so 3 is the poorest, and 9 is the highest quality. So they assign a quality to different wines, and they record the different characteristics of that wine. So we can use these features here to try to predict a wine in the future. So we can use this like a simple predictive model exercise. Okay, so first of all, in a machine learning task, you need to define the features. So the feature is what we saw before, is the 11 features on the left-hand side. So in H2O, you need to tell them that I want to use all these features. So you can say, I can use all the names of that table, of the data frame, excluding the last one, excluding the quality. Because if you can see that, if I exclude the quality column in there, then the rest will be the features that I want to use in the modeling exercise. So this is the code that I use. So at the end, you have a simple list here telling you about the names, the column names of the features that I want to use in this model. So, and then this is one of the really common tasks that you do for machine learning. You want to split the data into different parts. It's because if you use all the data to train your model, you can fall into a problem called overfitting. So you can memorize everything very well in that training data set, but the model doesn't generalize to the future problem, to other data. So what we want to do sometimes is to separate, just get a whole outset for testing, for further validations, and use the rest for training. And that's what we do here. So I'm using 80% of the data for the model training and hold out 20% of that for further testing. And that's how we do it in H2O. So we're using the split_frame function in H2O. And then you can specify a ratio. The ratio, the first number is 0.8. So H2O will automatically figure out the rest of the percentage. So you can just say, I want 80% for training. And then you have two data sets, 80% and 20%. Everything OK so far? Yeah, some basic stuff. So now this is the first algorithm that I want to show you and the usage of H2O GLM in here. So maybe you can't really see it from the screen. Maybe it's better on your laptop. So what we need to do first in Python is to, from H2O, we import the functions for GLM. So that's the GLM estimator you can see maybe on your screen. So, and then you need to tell H2O what kind of problem this is. So this is for regressions. So we use the family as a Gaussian for this problem. So if it is for binary classification or other problem, you will have to specify a different distribution or different family. So once you define the model, and then you go to using the train function, so you train with the X equals the features. The feature is the 11 value that we specify for this training. And then we look at the target, which is the quality of the wine that we want to predict. And we point to the data frame that we use. So it's the 80% that we take out, randomly take out for training. So that is the minimum API to do a GLM model in X2O. So when you execute that, so remember that when you execute this code, it's not using Python to do the computation. It's going to talk to H2O cluster in JVM and use the Java to do the computations. And then you can get the result back to Python when it's done. So for machine learning problems, so we need something to measure the performance. So there are many metrics in H2O that is already implemented for different problems. So I'll just want to pick one of the metrics in H2O. So we're using the mean squared error. So just if you have a lower error, then it's a better model. So what you do after you train the model is that you can just print it out in Python. You can just type the name or just print blanket the model, and it will get some basic information about the model. So it's like a summary of the model. You may not see everything, but this is like all the metrics that we calculate based on the model on the training data set. But this is only looking at the training data set. Sometimes it's not representative of the true performance of the model. So what we need to do next is to actually use this model and evaluate the model performance on the whole out 20% data set. And that's what we're trying to do in here. So we're using the model underscore performance function in H2O, and then you point it to the test data frame, and then it would do the same kind of metric calculations using the model on the test data set, and it will then give you more metrics. So that's a way to look at, okay, how good it is on the unseen data set. Okay, and the final steps. So once you have the model, what you want to do with the model is mainly about prediction. So you can now use a model to make predictions. So this is only using the same test data frame, but imagine this is like the future data set. So in your pipeline, when you have a new data coming into the system, you can convert that into the H2O data frame, and then use this function to make some predictions. So for example, this is a regression problem, so it just gives you some numbers. So if it's a classification problem that I will show later on, it will give you the predictor label and the probability of different cars. So for the regression, it's just a number, one column for the numbers. Okay. Everything okay so far? It's a simple GLM model, yeah, to make some prediction. Okay. So the next two slides, I'm just going to show you the API for different algorithms. So it's the same kind of theory, using the same data set, the training data set of 80% data, but we're using different algorithms. So the first one here on top is the random forest. We call it DRF because it's a distributed random forest. So you can see the API there. Again, you have to import the function from H2O. You set up the model. And then the final bit is the same. You just point it to the X, which is the features, the Y, the response, or the target, and the data frame. The same applies to GBM. Again, you import the function of GBM, set up the model, and then you do dog train of the model, and it will just give you the model. And finally, we have the same API for deep learning. Again, you import the function, do the same thing, but that will be using different algorithm in H2O to train your model in Java. Okay. Okay, so that is the basic for regression models. So is there any questions so far before I move on to a classification problem? You guys are smart, so you got no question at all, right? Cool. Okay, so I want to do the same basic stuff, but this time on a different data set. This time I want to do it for a classification problem. So we move on to the next notebook here, but actually it's a few ones down. It's number 4A, the classification basics. So we're going back to use the Titanic data set this time. So this time we want to predict whether the passenger survived or not in this tragedy. So you can see that the column is the second one. We mentioned that this is like an integer when you import the data into H2O. So what we need to do first is to convert that column from integer to categorical value, or enum in Java. So this is what we do. I also convert another things in another column in the datasets because the cars, I think that this is more suitable for categorical value instead of integer. So I converted two columns. from integer to categorical value. So this is the code to do that. And then do a simple table count to see how many values, how many unique values in different column. So then I also handpicked some features because I don't want to use all the features. Some of the features like the passenger names or other information that may not help the model. So I handpicked some of the features from that data set to build this model. And to do that, I just create a simple list in Python and just give them the name of different column. Okay. And the same thing that I did like the regression problem, I split it into 80% for training and 20% for validation or testing. Okay. So we move on to the first algorithm again, so GLM again. This time, remember, it's not for regressions. This time it's for binary classification. So you see that once you import the model, maybe on the screen, then you can see I accept the model in the family as a binomial. So this is like a binary classification family or distributions. So we have to define that. So H2O understand that I'm now doing a binary classifications instead of regressions. But then the rest is almost identical. So you point to the features. This time, the target is the survives column. And then you point to the data frame, you execute the code, and you train the model in H2O JVM. And so this time, because it's a different problem, so we're using different techniques or different metrics to measure the performance. So one of the really common ways to measure the performance of a classification problem is to look at the confusion matrix in here. So how many of you have heard about confusion matrix before? Okay, so I don't really need to explain a lot. So it's like how you visualize the problems in a matrix. So you have the true positive and the true negative in one diagonal, and the false ones in the other diagonal. So what we want to do is to optimize or to maximize the true negative and the true positive in this matrix. So that's what we got in H2O. So we have now we can have the model in GLM model, so we can print it out, so we can have the summary again. But this time, you also get the confusion matrix as the result in the summary. Because also we have other metrics to measure classification like log loss, so you can also see it from the table that there are lots of different measures. So we automatically calculate a lot of different metrics for you every time you train the model or you want to evaluate a new model. And then we can do the same thing on the test dataset. So we use the model underscore performance features to look at the model performance on the unseen test dataset, and then we give you some results like that. And finally, this is the time to make predictions. So say you are happy with this GLM model, you want to make some predictions. So you do the same thing, you point it to the dataset, you use the predict function in H2O, and this time it will not only give you one single column for the numerical values. This time it will give you 3 columns. The reason is that the first column is the actual predicted class, so it's either 0 or 1, so it's the survive column, 0 or 1, 2 class. But you also get the probabilities for each class. So that is quite useful sometimes, because sometimes you may have a model that's really, really confident on some predictions, but sometimes it's a bit uncertain on in some situations. So these numbers will give you another way to look at the predictions, so whether how confident you can feel on different predictions. Okay. So I just want to quickly show you the same kind of API for different algorithms. So again, we start with random forest on the top and GBM on the bottom. So what you need to do again is to import the function, set it up, and point to x, y, x the features, y the target, and the data frame. It's always the same. But of course, this is the basic usage of H2O. There are a lot more arguments that I can use in those algorithms to make it better. So which I will show you in the next session, is the advanced usage of H2O. And again, quickly about deep learning. So you just do the same thing, point to the deep learning functions and make predictions. And that is the end of the basic H2O usage. So the next session will be more about tuning the performance, so making it better, so making one of the algorithms better on dataset. If you want to take a break or ask me any questions, we can have like a 5-minute break, if that's okay with you guys. Yeah? Okay. So let's have a 5-minute break, and then you can also ask me any question during this time. Okay? Okay. So for example, I can use the number of trees, the n trees, so you can give the H2O model more time to train, so more number of trees when they build a model. You can also define a sample underscore weight, which is the random resample weight of different rows. Equally, we have the resample weight for different columns. So I put 0.9, which is 90% of that. So every time we include some of the randomness into the tree. So that actually helped the model to be more generalized to future data. So once you have the model from these settings, so this is my manual settings for this GBM, then again we can test the model on the unseen 20% data set. Then if you can see that this is now getting slightly better, so we have a lower MSE or mean square error this time, so which means the manual settings that I put into that model actually worked in this case. So it helped to reduce the error a little bit. But sometimes it's not enough to only look at the test data set, because maybe I just got lucky in this case. Maybe I just got lucky with this test data set. We want something, some extra measurements to help me to make decisions whether I make the correct settings on this model. So we move on to a technique called cross-validations. So how many of you have heard about cross-validations, K-fold theory? Okay, great. So you probably know about it. So the idea is that every time you train the model, you create a simple, a small whole data set. So we can see it from table. So from flow 1 to flow 5, every time we choose a random sample from that, take it out, to use that for extra measurement on the unseen test data set. So we call this the cross-validations. And after that, we use the average of that to give you another value to measure the performance of the model on unseen data set. So once we have that, we want to do that in H2O. It's quite easy. So what you need to do is to include one more argument in that. So you can see maybe on the screen, the final argument is called n flows, so the number of flows equal 5. So you can do, usually I'll do 5 flows, or if you don't have enough time, you can do 3, so 5, or even 10 or 20 if you have more time. So we could give you more accurate measurements. So this time I use 5, so it means that it will do the same thing as I saw on this graph. You will create 5 different flows to do the cross-validations. So that's all you need in H2O. So just define the number of n flow, and we'll do the training in the back end. But I didn't change the settings for the sample weight and the column sample weight. So this, you should expect you will have the same performance on the test data set, because I didn't change anything in the settings. I only asked H2O to create the cross-validations for me to look at the different measurements. So let's look at that. So when you print out the model, you can see that there's another matrix table there. And the top one is the average of the MSE across the 5 cross-validation. And now if we go back to the summary table, you can see that we have another value in there for cross-validations. So now we have another measurement as a baseline. So say from this point, I want to measure the cross-validation as well in terms of performance of the model on unseen data set. So I have 2 measurements, one on the cross-validations and one on the test data set. Everything okay so far? Yep. So next step I want to do is to include another technique called early stopping. Have you heard of early stopping before? Yeah. So let me just explain it. So sometimes when you train the model long enough, say for example GBM, the gradient boosting machines, if you have given it a high number of trees, you can memorize everything about the training data set, and we cause overfitting. So as you can see that there's the graph there. If you look at the training data set, the error, the mean square error will just go down all the way down to nearly 0, because we're just trying to use the algorithm to memorize everything happened in the past. But that may not generalize well on the unseen data set, as you can see that on the data curve there. So at some point, the performance on the test data set will deteriorate, and we don't want that. So we want to find out that sweet spot, the where to stop that. So we don't want to train the model for too long. We want to stop that where we want to find a sweet spot that the test performance is just right, it's just perfect, and then before it goes to deteriorate. And that's what we want to do in this step. We want to find a sweet spot. So what you need to do in H2O, if you look at the screen, is to include some extra arguments to tell H2O that we want to do an early stopping. So we want to tell H2O I want to look at the metric MSE, which is mean square error in this case. we look at 15 rounds, so meaning that every time we find a new, the best performance on a test set, we'll go for another 15 round, 15 trees in this case, and see if it still go up for 15, after 15 trees, it will just go back to the sweet spot and stop there and use that as the best model for that case. So that's what we have here, and then so once you run this model, and then the HDO will just start looking at the performance every time. And once we have found a sweet spot, this time we find that the trees number is 155. So that is the sweet spot that we want to stop the model here. So that is using HDO to this job automatically for you in the background. So make sure that you can just get the best model at that point in time. So once we have this model using early stopping, then we can again look at the performance on both course validations and the test data set. And now you can see that for both measurements, so for the course validation measurement and then the test net, we both gone down a bit, slightly gone down a bit. So that is a good, good indication that this is working, because now you're not only looking at one measurement, you're looking at both measurements on course validations and tests. So that is giving you more confidence that this technique is working on this model. Okay? Everyone okay so far? Yeah? Okay. So the next step, I show you how to use early stopping, but that's only based on the manual settings I gave. So the manual setting for sample weight, 0.9, and the column sample weight, 0.9, 90%, but that's only based on my experience. Sometimes it doesn't work for all the data set. We want to use HDO to actually do a grid search and look for more options, more combination of different settings. And that's what the next step is, about grid search. I just create a very simple table here to look at different options in sample weight. We sample weight for rows, and then we sample weight for columns. But you can see that even for like 3 parameters in each options, it will give you a total of 9 combinations of model that you may have to search. So imagine that if you have a different kind of strategy, so you want to expand the search space for more, so we want to include another parameters in there, then you can expect that the search space will go exponentially if you have a really compact search space. But let's look at a small search space like this, like 9 models in H2O. Let's go through them all in H2O. So what you need to do in H2O is the code that you can see on the screen, is to ask H2O, okay, this is the search space I have. So 3 parameters for the column sample weight, 3 for the sample weight for rows. I want to look at all of them. So I want to use the strategy of Cartesian, that means the full research of everything that you have in that search space. And then you use the H2O research function in H2O to look at the GBM model in this time. So this time, when you execute a model, it will do all the things behind to look at different. So every time you change the parameters in different settings based on the list that you supply there, and we go through all different 9 models for you and give you the performance, the metrics for different settings. So then you can now print out the table. So if you go to the next page, then you can see that this is now giving you a more evidence for you to decide whether a setting is good or not for this model. And you can tell from the MSE, so the mean square error, from this table. So it's saying that in this case, we're saying that for the column sample weight, we should use 0.8, and for sample weight, we should use 0.9, which is 90%. So that will give us the lowest MSE in this case. So that is good. So now I'm not using my own experience to judge whether this model is good or not. I'm using more evidence from different experiments in H2O to tell me more about the different settings and the impact on this data set. So after that, again, you can just extract the best model, and then you can use it, and then you can test again on the test data set. And if you look at the table again, we got a much better result this time, so we can also reduce the mean square error in course validations as well as the test data set. So this is like step by step to improve the model. So of course, once you've done this workshop, you don't have to go through this every step, every time. You can just go through the final step. But I just want to show you the logic behind every additional features in H2O and how they improve the performance on the model. Okay, so far? Any questions? Okay, so Okay, so the next step here is about the search space. How to reduce the search space? So I'll talk about the grid search. So, yep, that's a question. Please wait. There's a mic coming out. Yeah. Is it this line?
Yes, on that one. So I was surprised that the mean squared error on the folds was higher than the mean squared error on the test set consistently.
Okay, because they're not exactly the same thing. So the cross validation is looking at let me go back to here. So the cross validation data set is based on the random resampling inside the training data set. So we're not looking at exactly the same data when we do the cross validation and the test. So you could get luckier on the test data set, which is the training set that we took out earlier. And you may get a worse performance on the cross validation. But the point is to compare step by step when you add different features in H2O to make it better. Does it reduce the error in both cases? And that's the main theory of this. So you don't have to compare them like apple to apple because they're not apple to apple. But you compare to the previous features that you add to the step. Is that clear?
Yes.
Okay.
But the test is just one of the cross validations, right?
No. The test is, let me just go back to. So the test is before we start everything, because we start the cross validation, we take out 20%, just leave it forever like that. And the cross validation is within that 80%, so that's why they're not apple-to-apple comparisons. Any more questions before I move on? Okay. Let's go back to... Yeah, so we talk about this grid search. So this one is a simple one with 9 different combinations. So what if we want to expand this search space to a bit bigger? So this is what we want to do in this situation. So now I want to include another parameters in there is the depth of different trees. So the trees, you can do decision trees, you can go different depth. So I want to search another 3 depths, so 3, 5, and 7. So that adds into another complexity to the search space. So it makes about 27 combinations in total, so another 3 times of the original search space. But say, okay, this is a toy data set. You can run it quickly, even if it's 27 combinations. But what if you have a much more complex search space and then you don't have enough power on a big data set? You may want to reduce the size of search to a number that you can handle. So maybe it could be a time, or could be a number of models that you could handle with your hardware within a certain time frame. And that's what we're doing here. We want to, so out of these 27 combinations, we only want to search for 9 combinations, for example, this case. I don't want to look for all of the combinations. I want to take a random 9 combinations of that search space and do the same kind of research in H2O and see if I can find a better solution to this problem. So that's the code in there. You can see it on the screen. And then, so once we did that, then H2O will just randomly, based on a random seed, pick 9 of the combinations from the 27th and do the same grid search that we saw before. So this time we can see that we have, on the first table there are 3 columns of different settings. So we have the sample weight for columns, sample weight for the rows, as well as the max depth. So this is getting, so it's a bigger search space than before. So we're expanding the search to more, a bigger territory and see if we can find better solutions in that search space. And we did. So we can see that now we can compare the new metrics on the cross validations and on the test set and compare that with the previous full search. But remember that full grid search is based on a smaller search space. This one, although we have the same kind of 9 model grid search, but we're looking at a much bigger search space in here because we include the max depth in this search space. So we managed to find a better solutions in this time. So we also reduce both metrics in this case. Okay, so everyone okay so far? So that's the random search. So this is one of the most practical way to do in the data mining competitions. So you don't have time to go through all the combinations that you want to search in the search space. This is the most practical way to do a practical search on some good settings for your model in a reasonable amount of time. So please remember to use this step. So when you are moving on from this workshop to your own problems, use these steps to get some good settings for your data. Okay, so the last one is the even more advanced techniques to combine different models together. So the previous steps is only based on one algorithm, so the GBM, the gradient boosting algorithm. But for data mining competitions like Kaggle, you want to combine different models of different algorithms. Like you want to have a larger diversities of the models to capture different things in the data and then combine them together quickly. So we create features in H2O called Stat Ensemble. So this is the next notebook now, so it's the 3B, so regressions ensembles. So mainly this is based on the work from Aaron and Dell. Aaron and Dell did a PhD on stacking models. So this is one of the very useful way to improve performance quickly without doing a lot of feature engineering. And this also works for Marios. Marios, if you know him, he's the top Kaggler. So he was the former #1 Kaggler in this competition, in this platform. So he also joined H2O. So thankfully, we have him to bring his experience into H2O to improve this stacking as well. So he has his own software called StatNet. So he's really experienced in stacking models. So that actually worked for him, and he actually won a lot of competitions using stacking. So this is one of the techniques that you may want to use it if you want to join the Kaggle competition. So back into the H2O, so how do we do the stacking simply in H2O? So first of all, I want to show you the same thing that we have done before. So just do a random grid search on GBM this time. So using the random grid search to look for a good model, or the best model using a GBM algorithm, and then just use that for the future. And the next two steps is almost the same, but I'm using a different algorithm this time. So we're using random forest this time. You can see that the settings and the search space on different parameters are different, but the underlying idea is the same. So do a random grid search for this algorithm and get the best model for that, and then move on to the next algorithm. So the next algorithm is the deep learning algorithm in H2O. So again, you will provide a different search space, do a random grid search, and get the best model. So now I have 3 best models from the 3 different random grid search. And I want to use this stat ensemble function in H2O to stack them together quickly and to give me much better performance than before. So that's what the main API for model stacking in H2O. So first of all, you list the model together. So you create a list in Python. That's the list of the model, the best model from the 3 previous research. That's the best GBM model, the best random forest model, and the best deep learning model. So once you have that, you can set up the stat ensemble, which is the second part of the code, maybe on your screen. And then you do a train function again, similar to other train functions. So you put on X features, Y equal the target, and then the data frame. And we will do all the clever stacking in the backend. So you don't really see anything complicated in this environment. You just see it running everything in the backend. But it's also doing some really, really sophisticated stacking in the backend at H2O. So we're trying to use the cross-validation results from different models, but they become new features, and then we stack them together like a meta training on those features. And that will give you, if you can see that from the table here, we get a better MSE or lower MSE comparing with the best model of each algorithm. So once we have that, we can go back to the table. So we didn't do the cross-validations measurement this time, but we can see that the performance on the test data set is, again, better than all the previous steps. So this is some of the ways that you can do with your data set. So when you put in H2O import data set, you can train different models and you can stack them together quickly using this code. Okay, so any questions so far? This is the ensemble for regressions. Yes? Oh, not yet, but we are looking at more different ways to export more information from this ensemble. So for now, I understand what you mean. So we say, okay, how different is the algorithm from GBM, the model of GBM, contribute to the ensemble than random forest and deep learning? That we can, if you can imagine, the first step we want to try to do is to simplify the step. So everything is like in the back end. But the next step here is to give user more ability to extract the information out of that process. So that will be the next version. maybe a future version. But for now, it's just a simple training exercise to get everything together. But if you can do it manually, if you want to do it manually, what you need to do is to extract the cross validation predictions from different algorithms and do your meta training yourself, and that you can have more say or more information about which algorithm contribute more to the final ensemble. But that's the manual way to do it. We don't want the user to do that for now, but in the future we want to have more functions to export the information. Okay. Any more questions before I move on to the next example? Yeah.
You stack 3 models?
Oh, sorry, I have to wait for it.
So you stacked 3 models, and you got the best performance. And would it be possible that if you stack only 2 models, that the performance might be better?
Yeah. So this is the good thing about H2O. It's easier for you to change that. So for example, if you want to just choose 2 models, what you need to do here is to change the list in the top, so you can see that it's the list. But you only need to choose.
If you have like 10 models or something, then you would check like 10 models, stack 10 models, then 9,
I understand
8,
what you're saying. Yeah.
And then you have to check all the combinations.
Yeah. So what we can do this is a programming language. You can do a loop to go through that, or you can just believe in H2O, because the way that we do the meta training is the same. So it's kind of like feature selection in the same time. So we're using the meta learning to look at which model the features from the different algorithms should contribute more. So that is kind of automatically done. But of course, I understand that sometimes if you exclude some of the models, it may get you to a better performance. But you can do it quickly by just changing the list in there, using a for loop or other ways to do it. And then H2O will just look at smaller selection of the model, give you the same performance metric, and then you say, oh, okay, maybe that is better. Okay? Any more questions about this? Okay, so I just want to move on to the same kind of principles, but this time it's on a different problem. So we're going back to the Titanic. So it's a binary classification problem. So again, this is a new Jupyter notebook, so 4B, and then classification ensembles. So I won't go into much details, but it's the same kind of principles. I want to train GBM model or gradient boosting model on the Titanic dataset, and I want to train random forest again on that same dataset using random grid search. So now I have 2 good models, so one good GBM and one good random forest model. I want to combine them, but this time I want to create a model for classifications. So you can see that maybe on your screen that this is the same kind of API to do the stack ensemble in H2O, but we are using a different metric this time. We're using the AUC, the area under curve this time, so the higher is better. So you can see that in the final table that the individual model will give you about 8.8 or 0.88 or 0.89, but the final one is a bit improvement based on the combination of 2 models. So back to the same question that this gentleman asked. So you can have hundreds of models when you do your example. This is only show you the toy example with 2 models in here. But in practice, you can use H2O to give you more models. So from the grid search, you can extract all the models from that grid search. We'll give you 10, 20, 50 models from different algorithms. And then you can combine everything together as long as you can create that list to capture all the names of the models. And H2O will just go through all the features in those, or generate from those models, and give you the stack ensemble at the end, quickly in a simple API like this. Okay. So that really is the stacking for classification. So if you want to tune it, you can just expect the same step like I showed you in the regression problem. So you can use cross validation, early stopping, and grid search, random grid search or full grid search, and then finally the stack ensemble to tune it. So this is showing you that's the final step. So usually, if after this workshop, you don't have to go through all the steps again. You can just go through maybe the final step using the stack ensemble, and usually that will give you a really, really good model for any purpose. Okay. So final thing I want to show is, so I'm showing you how to use all this on your computer, on a single computer. Sometimes you want to say you want to deploy H2O in the cloud because you want to go to maybe Amazon, it could be Google Cloud, from a much a beefier server or much powerful machines with more CPU core. So all you need to do is to deploy H2O using the Java command. So I can show you live in here. So first of all, you can go back to H2O, download just get the pure Java version of H2O, extract that on that server, on that cluster. Could be a Linux server, could be a Windows or other platform server. As long as you have Java 1.7 or above installed on the machines, and this will work. So let me just show you how to do that. So for example, I just download that zip here. This is the latest version of H2O. So when you download that, it's a zip file that I can put on anywhere. So I put it on the desktop here. And that's the folder that I extract that. So when you open that, you see this is what is inside that zip file. So all you need to do, if you can see here, you need this jar. So H2O.jar is the file that you need to create a cluster, whether on a computer or whether on a remote machine. So let's imagine if this is like a cluster in the cloud. So if I open it in terminal, let me just make it bigger. Okay, can you guys see it? Yeah, roughly. So if I go back to this page here, you can see that the command here is java-jar and then h2o.jar. So if I do that here, so java jar h2o.jar. So when I execute this command, it will create a cluster, so the actual cluster on this machine. So for example, now it's on my desktop or on my laptop. But imagine if you do the same thing in a remote machine in the cloud, then you can have the power in the cloud with H2O on. So, but how do you connect to that cloud? So you need the IP address and the port. So what you need to do is look at the information here, because I changed the font size so you can't see it clearly. But usually is the IP address and the port is 54321. So what we can do to connect to this server here is going back to this page. Let's just go back to this page. So once you have that cluster deployed somewhere on the cloud, all you need to do supply to H2O is the IP address of that machine. So in Python, after you import H2O module, this time you use the h2o.connect command. So you supply the IP address of that, and then it will use a connection to communicate from your machine to that H2O cluster in the cloud. So you can utilize that more power from the cloud to deal with a much bigger problem. And that's how we do it H2O in the cloud. Is everyone okay so far? Yes.
So actually, what is the difference between using running a Jupyter notebook in a multi-core machine server and then using that particular IP address in my machine, because that also uses the same power, right? So what is the difference between using kind of H2O with multiple core possibilities and running a Jupyter notebook in a multi-core machine and then using the same IP address to run the Jupyter notebook service in my machine to use the H2O in my machine?
Oh, so say if you have Jupyter already deployed on that machine, you don't have to do this step. So this is like for your machine. So if you want to use Jupyter on your own machines, but you want to connect to the actual cluster that is in the cloud, then you do this step. So if you already have Jupyter deployed in the cloud, you can just do H2O initiate. So without the IP address, you will just do the initiation in that cloud. Then your Jupyter notebook in the cloud can automatically detect that actual cluster in the cloud.
Okay.
Yeah. So this is only for if you want to use your own machines away from the cloud to do that. So there are different ways to connect to H2O. Oh, speaking of which, I want to show you that now. So now I have this H2O cluster here on my laptop. I just want to quickly show you how you can connect it to that cluster using a web browser. So because it's my own machine, so it's localhost or 127.0.0.1, you give it the address here. And then this is the first page that you will see for the H2O flow interface. You can do something simple, but for example, if I want to get the data, you can just browse to say this is the same kind of wine quality CSV we've been using. You select that. You upload to that, and let me just. it'll give you some options to change the type. So for example, this is all numeric, so it's okay. But for example, maybe if you want to change maybe the quality column to categorical, you can change it to item here. So that's something that you can ask your colleague or your friends if they don't want to use Python or now to do with Xcode, they can use the web browser to do the same thing. And then you parse that. Then this CSV is imported to the memory of the Xcode cluster. And you can also do this very quick, like a visualization here. So for example, you can look at some of the columns here, see the distribution of this column. So this is a way to quickly like prototyping some of the data sets into your Xcode cluster and just have a look around, play around. So there are different ways to use H2O.
So you're saying that if I'm actually running the h2o.jar in, for example, like a 40-core cluster, 40-core machine, and I'm actually using that particular local host in my machine, then here I can actually make use of those 40-core cores, right?
So you supply the different IP address. So you actually use the IP address in the cloud this time to connect to that machines, and then you will have the power of that cloud server for 40-core machines. So you can do the same thing. You can upload the data set into the memory. So providing you have a good network connection to that, and all computations is done in the cloud with the 40 cores instead of your computer.
And do I need to SSH into that particular, or just running the H2O cluster is actually good enough to connect with it?
Yeah, so all you need, of course, is the Java. So Java 1.7 or above, or OpenSDK. So or OpenJDK, sorry. If you have that as a base requirement in the cloud cluster, that's all you need. And then you can download H2O, the zip file that I showed you before, download to that cluster, unzip it, and just Java-jar, H2O jar, and that will just initiate the cluster in the cloud.
Yeah, thank you.
Please.
I'm a little bit confused about the terminology you're using. So you say cluster the whole time, but the examples actually show a single multi-core machine.
Yep.
Can I get, say, 25, 40-core machines and
Yes.
run H2O on that?
Yes. So what I show you here, this is a cluster on its own. This is a cluster using my own laptop. So 8 virtual core or a quad-core CPU, so 8 virtual core, and I assign some memory to it. But if you want to use multiple clusters, so maybe another laptop here. So if I have another laptop, I can initiate the H2O again here. All I need to do is to provide a list of IP address. So I have the IP address for this one, and they can communicate each other. And they will share the CPU power, a CPU resource, and the memory. So you're maximizing the resource that you have. So at home, I do like multiple laptops together in a home network. So provided you have a good connection between them, then you can just start cluster in different laptops and work together. And that's beautiful of H2O. Yes, please.
If you say all you got to do is to give it a list of IP addresses, does that imply that the local machine you're working on does the role of the master node?
Yeah, there's no, so in H2O, there's no specific master log. So it's unlike Hadoop Spark. Everyone share the data and algorithm training. So they're using the same kind of, the API that you use in Python in R is the same like the single cluster. But when you execute it, it will automatically distribute the job, the workload, to all different machines that is in that kind of setup. And you don't have to, the user will not have to specify which one will do that one, which one will do the other job. You just automatically do it in the backend.
So you're handling down the list so all nodes can communicate with all other nodes?
Yeah.
Okay.
You can also say that, maybe you can kind of say that your control, your desktop or your laptop is kind of the master to execute a command. But that's only using the interface to tell the H2O cluster to do some work. But it's not actually a master in a way as Hadoop or Spark.
Okay.
It's 5:30, so we should start moving to the next
Okay, so
tutorial.
I'll just wrap up quickly and just a few more slides. That's it. So a quick recap. So in this workshop, I just want to show you how to use H2O, the basic usage and some advanced usage. So hopefully that after this workshop, you can start H2O cluster from Python. You know how to import some data set CSV or from internet into H2O. And then you can do some basic transformation, train some regression model, classification model, improve the performance using different techniques in H2O. And if you want to use much more powerful machines in the cloud, you can do that, hopefully. And the summary here is that I'll show you how to use H2O functions, different functions in H2O to improve the performance step by step. And if you want more information, remember this is the address I want you to remember. So it's documents, docs.h2o.ai. Then you can find more code, more tutorial, more examples from that web page. There are also more ongoing stuff of H2O. So I'll be here around for the weekend. So if you want to ask me about other things happening at H2O, please give me a shout. So finally, thank you for having me again in Berlin. I really love to be here. If you want to contact me, this is my contact info. You can also find all the information for the previous or on the future meetups of H2O using that link there. If you want to search questions on Stack Overflow, please let me remind you that you use H2O as a tag instead of H20, because if you put H20, sometimes you get to the wrong question. So H2O is a tag that you need for Stack Overflow. So thank you very much.